brown dwarfs are substellar objects too low in mass to sustain hydrogen-1 fusion reactions in their cores, unlike main-sequence stars. They occupy the mass range between the heaviest gas giants and the lightest stars, with an upper limit around 75 to 80 Jupiter masses. Brown dwarfs heavier than about 13 megajoules are thought to fuse deuterium, and those above 65 megajoules fuse lithium as well. Brown dwarfs may be fully convective, with no layers or chemical differentiation by depth. The defining differences between a very low-mass brown dwarf and a giant planet are currently being debated. One school of thought is based on formation. The other, on the physics of the interior. Part of the debate concerns whether brown dwarfs must, by definition, have experienced fusion at some point in their history. Stars are categorized by spectral class, with brown dwarfs being designated as types M, L, T, and Y. Despite their name, brown dwarfs are of different colors. Many brown dwarfs would likely appear magenta to the human eye, or possibly orange-red. Brown dwarfs are not very luminous at visible wavelengths. Some planets are known to orbit brown dwarfs: 2M1207b, MOA 2007b LG 192 pounds, and 2MASS J044144b, at a distance of about 6.5 light-years. The nearest known brown dwarf is Lumen 16, a binary system of brown dwarfs discovered in 2013. One brown dwarf, Dennis PJ 82300.1-491201b, from an ultra-cool binary system, has a mass of about 28 Jupiter masses, making it the largest known exoplanet. History. The objects now called brown dwarfs were theorized to exist in the 1960s. They were originally called black dwarfs, a classification for dark substellar objects floating freely in space that were too low in mass to sustain hydrogen fusion. However, the term black dwarf was already in use to refer to a cold white dwarf. B. Red dwarfs fuse hydrogen, and C. These objects may be luminous at visible wavelengths early in their lives. Because of this, alternate names for these objects were proposed, including planetar and substar. But in 1975, Jill Tarter suggested the term brown dwarf, using brown as an approximate color. This has been the name used in astronomy ever since. The term black dwarf still refers to a white dwarf that has cooled to the point that it no longer emits significant light. Early theories concerning the nature of the lowest mass stars and the hydrogen burning limit suggested that a population I object with a mass less than 0.07 solar masses or a population II object less than 0.09 solar masses would never go through normal stellar evolution and would become a completely degenerate star. The first self-consistent calculation of the hydrogen-burning minimum mass confirmed a value between 0.08 and 0.07 solar masses for population I objects. The discovery of deuterium burning down to 0.012 solar masses and the impact of dust formation in the cool outer atmospheres of brown dwarfs in the late 1980s brought these theories into question. However, such objects were hard to find because they emit almost no visible light. Their strongest emissions are in the infrared spectrum, and ground-based IR detectors were too imprecise at the time to readily identify any brown dwarfs. Since then, numerous searches by various methods have sought to find these objects. These methods included multicolor imaging surveys around field stars, imaging surveys for faint companions to main-sequence dwarfs and white dwarfs, surveys of young star clusters, and radial velocity monitoring for close companions. For many years, efforts to discover brown dwarfs were fruitless. In 1988, however, University of California, Los Angeles professors Eric Becklin and Ben Zuckerman identified a faint companion to a star known as GD165 in an infrared search of white dwarfs. The spectrum of the companion GD165b was very red and enigmatic, showing none of the features expected of a low-mass red dwarf star. It became clear that GD165b would need to be classified as a much cooler object than the latest M dwarfs then known. GD165b remained unique for almost a decade until the advent of the 2-micron all-sky survey when Davy Kirkpatrick, of the California Institute of Technology, and others discovered many objects with similar colors and spectral features. Today, GD-165b is recognized as the prototype of a class of objects now called L-dwarfs. Although the discovery of the coolest dwarf was highly significant at the time, it was debated whether GD-165b would be classified as a brown dwarf or simply a very low-mass star, because observationally it is very difficult to distinguish between the two. Soon after the discovery of GD-165b, other brown dwarf candidates were reported. Most failed to live up to their candidacy, however, because the absence of lithium showed them to be stellar objects. True stars burn their lithium within a little over 100 mi, whereas brown dwarfs will not. In other words, the detection of lithium in the atmosphere of a candidate object ensures that, as long as it is older than the relatively young age of 100 mi, it is a brown dwarf. In 1995, the study of brown dwarfs changed substantially with the discovery of two incontrovertible substellar objects, which were identified by the presence of the 670.80 nm lithium line. The most notable of these objects was the latter, which was found to have a temperature and luminosity well below the stellar range. Remarkably, its near-infrared spectrum clearly exhibited a methane absorption band at 2 micrometers, a feature that had previously only been observed in the atmospheres of giant planets and that of Saturn's moon Titan. Methane absorption is not expected at the temperatures of main-sequence stars. This discovery helped to establish yet another spectral class even cooler than L-dwarfs, known as T-dwarfs, for which Gliese 229b is the prototype. The first confirmed brown dwarf was discovered by Spanish astrophysicists Rafael Rebelo, Maria Rosa Zapatero Osorio, and Eduardo Martín in 1994. They called this object Tide 1 and it was found in the Pleiades open cluster. The discovery article was submitted to Nature in spring 1995, and published on September 14, 1995. Nature highlighted brown dwarfs discovered, official in the front page of that issue. Tide 1 was discovered in images collected by the IAC team on January 6, 1994 using the ATS-CM telescope at Tide Observatory, and its spectrum was first recorded in December 1994 using the 4.2M William Herschel telescope at Roque de los Muchachos Observatory. The distance, chemical composition, and age of Tide 1 could be established because of its membership in the young Pleiades star cluster. Using the most advanced stellar and substellar evolution models at that moment, the team estimated for Tide 1 a mass 55 times the mass of Jupiter, which is clearly below the stellar mass limit. The object became a reference in subsequent young brown dwarf-related works. In theory, a brown dwarf below 65 Jupiter masses is unable to burn lithium by thermonuclear fusion at any time during its evolution. This fact is one of the lithium test principles to examine the substellar nature in low luminosity and low surface temperature astronomical bodies. High-quality spectral data acquired by the Keck 1 telescope in November 1995 showed that Tide 1 had kept the initial lithium amount of the original molecular cloud from which Pleiades stars formed, proving the lack of thermonuclear fusion in its core. These observations confirmed that Tide 1 is a brown dwarf, as well as the efficiency of the spectroscopic lithium test. For some time, Tide 1 was the smallest known object outside the Solar System that had been identified by direct observation. Since then, over 1,800 brown dwarfs have been identified, even some very close to Earth like Epsilon Indi Bar and BB, a pair of brown dwarfs gravitationally bound to a Sun-like star around 12 light-years from the Sun, and Lumen 16, a binary system of brown dwarfs about 6.5 light-years away. Theory. The standard mechanism for star birth is through the gravitational collapse of a cold interstellar cloud of gas and dust. As the cloud contracts it heats due to the Kelvin-Helmholtz mechanism. Early in the process the contracting gas quickly radiates away much of the energy, allowing the collapse to continue. Eventually, the central region becomes sufficiently dense to trap radiation. Consequently, the central temperature and density of the collapsed cloud increases dramatically with time, slowing the contraction, until the conditions are hot and dense enough for thermonuclear reactions to occur in the core of the protostar. For most stars, gas and radiation pressure generated by the thermonuclear fusion reactions within the core of the star will support it against any further gravitational contraction. Hydrostatic equilibrium is reached and a star will spend most of its lifetime fusing hydrogen into helium as a main sequence star. If, however, the mass of the protostar is less than about 0.08 solar mass, normal hydrogen thermonuclear fusion reactions will not ignite in the core. Gravitational contraction does not heat the small protostar very effectively, and before the temperature in the core can increase enough to trigger fusion, the density reaches the point where electrons become closely packed enough to create quantum electron degeneracy pressure. According to the brown dwarf interior models, typical conditions in the core for density, temperature and pressure are expected to be the following. This means that the protostar is not massive enough and not dense enough to ever reach the conditions needed to sustain hydrogen fusion. The infalling matter is prevented, by electron degeneracy pressure, from reaching the densities and pressures needed. Further gravitational contraction is prevented and the result is a failed star, or brown dwarf that simply cools off by radiating away its internal thermal energy. High-mass brown dwarfs versus low-mass stars. Lithium is generally present in brown dwarfs and not in low-mass stars. Stars, which achieve the high temperature necessary for fusing hydrogen, rapidly deplete their lithium. This occurs by a collision of lithium-7 and a proton producing two helium-4 nuclei. The temperature necessary for this reaction is just below the temperature necessary for hydrogen fusion. Convection in low-mass stars ensures that lithium in the whole volume of the star is depleted. Therefore, the presence of a lithium line in a candidate brown dwarf spectrum is a strong indicator that it is indeed substellar. The use of lithium to distinguish candidate brown dwarfs from low-mass stars is commonly referred to as the lithium test, and was pioneered by Rafael Rebelo, Eduardo Martin and Antonio Magazzu. However, lithium is also seen in very young stars, which have not yet had enough time to burn it all. Heavier stars, like the Sun, can retain lithium in their outer atmospheres, which never get hot enough for lithium depletion, but those are distinguishable from brown dwarfs by their size. On the contrary, brown dwarfs at the high end of their mass range can be hot enough to deplete their lithium when they are young. Dwarfs of mass greater than 65 Jupiter masses can burn off their lithium by the time they are 500 million years old, thus this test is not perfect. Unlike stars, older brown dwarfs are sometimes cool enough that, over very long periods of time, their atmospheres can gather observable quantities of methane. Dwarfs confirmed in this fashion include Gliese 229b. Main sequence stars cool, but eventually reach a minimum bolometric luminosity that they can sustain through steady fusion. This varies from star to star, but is generally at least 0.01% that of the Sun. Brown dwarfs cool and darken steadily over their lifetimes. Sufficiently old brown dwarfs will be too faint to be detectable. Ion rain as part of atmospheric convection processes is possible only in brown dwarfs, and not in small stars. The spectroscopy research into ion rain is still on the ingiro, and not all brown dwarfs will always have this atmospheric anomaly. In 2013, a heterogeneous ion-containing atmosphere was imaged around the B component in the close Lumen 16 system. Low-mass brown dwarfs versus high-mass planets. A remarkable property of brown dwarfs is that they are all roughly the same radius as Jupiter. At the high end of their mass range, the volume of a brown dwarf is governed primarily by electron degeneracy pressure, as it is in white dwarfs. At the low end of the range, their volume is governed primarily by Coulomb pressure, as it is in planets. The net result is that the radii of brown dwarfs vary by only 10–15% over the range of possible masses. This can make distinguishing them from planets difficult. In addition, many brown dwarfs undergo no fusion. Those at the low end of the mass range are never hot enough to fuse even deuterium, and even those at the high end of the mass range cool quickly enough that they no longer undergo fusion after a period of time on the order of 10 million years. X-ray and infrared spectra are telltale signs. Some brown dwarfs emit X-rays. And all warm dwarfs continue to glow tellingly in the red and infrared spectra until they cool to plant-like temperatures. gas giants have some of the characteristics of brown dwarfs. For example, Jupiter and Saturn are both made primarily of hydrogen and helium. Like the Sun, Saturn is nearly as large as Jupiter, despite having only 30% the mass. 3 of the giant planets in the Solar System emit much more heat than they receive from the Sun, and all 4 giant planets have their own planetary systems their moons. Brown dwarfs form independently, like stars, but lack sufficient mass to ignite as stars do. Like all stars, they can occur singly or in close proximity to other stars. Some orbit stars and can, like planets, have eccentric orbits. Currently, the International Astronomical Union considers an object with a mass above the limiting mass for thermonuclear fusion of deuterium to be a brown dwarf, whereas an object under that mass is considered a planet. The 13 Jupiter mass cutoff is a rule of thumb rather than something of precise physical significance. Larger objects will burn most of their deuterium and smaller ones will burn only a little, and the 13 Jupiter mass value is somewhere in between. The amount of deuterium burned also depends to some extent on the composition of the object, specifically on the amount of helium and deuterium present and on the fraction of heavier elements, which determines the atmospheric opacity and thus the radiative cooling rate. The extrasolar planets encyclopedia includes objects up to 25 Jupiter masses, and the exoplanet data explorer up to 24 Jupiter masses. A sub-brown dwarf or planetary mass brown dwarf is an astronomical object formed in the same manner as stars and brown dwarfs but that has a mass below the limiting mass for thermonuclear fusion of deuterium. Some researchers call them free-floating planets while others call them planetary mass brown dwarfs. Sub-brown dwarfs are formed in the manner of stars, through the collapse of a gas cloud, but there is no consensus amongst astronomers on whether the formation process should be taken into account when classifying an object as a planet. Free-floating sub-brown dwarfs can be observationally indistinguishable from rogue planets that originally formed around a star and were ejected from orbit, and on the other hand a sub-brown dwarf formed free-floating in a star cluster may get captured into orbit around a star. A definition for the term sub-brown dwarf was put forward by the IAU Working Group on Extrasolar Planets, which defined it as a free-floating body found in young star clusters below the lower mass cutoff of brown dwarfs. Lower mass limit: the smallest mass of gas cloud that could collapse to form a sub-brown dwarf is about 1 megajoule. This is because to collapse by gravitational contraction requires radiating away energy as heat, and this is limited by the opacity of the gas. A 3 megajoules candidate is described in the paper. List of possible planetary mass brown dwarfs, orbiting one or more stars. There is no consensus whether these companions of stars should be considered sub-brown dwarfs or planets. WD 0806-661b, DT Virgin is C, FW Tauri b, ROX is 42bb, orbiting a brown dwarf. There is no consensus whether these companions of brown dwarfs should be considered sub-brown dwarfs or planets. The 5 Euro 10 megajoules companion of 2 mass J04414489 plus 2,301,513, 2M1207b, free-floating, WISE 0855 Euro 0714 between 3 to 10 MJUP about 7 light-years from Earth. SRE 52, UGPS J72027.51-054031.2, Car 110,913 to 773,444, CFBDSIR 2149-0403, OTS 44, Observations, Classification of Brown Dwarfs, Spectral Class M. There are brown dwarfs with a spectral class of M6.5 or later. They are also called late M dwarfs. Spectral class L. The defining characteristic of spectral class M, the coolest type in the long-standing classical stellar sequence, is an optical spectrum dominated by absorption bands of titanium, 2, oxide and vanadium, 2, oxide molecules. However, GD165b, the cool companion to the white dwarf GD165, had none of the hallmark TO features of M dwarfs. The subsequent identification of many field counterparts to GD165b ultimately led Kirkpatrick and others to the definition of a new spectral class, The L dwarfs, defined in the red optical region not by weakening metal oxide bands, but strong metal hydride bands and prominent alkali metal lines. As of 2013, over 900 L dwarfs have been identified, most by wide-field surveys, the 2-micron all-sky survey, the Deep Near-Infrared Survey of the Southern Sky, and the Sloan Digital Sky Survey. Spectral Class T. As GD165b is the prototype of the L dwarfs, Gliese 229b is the prototype of a second new spectral class, the T dwarfs. Whereas near-infrared spectra of L dwarfs show strong absorption bands of H2O and carbon monoxide, the NIR spectrum of Gliese 229b is dominated by absorption bands from methane, features that were only found in the giant planets of the Solar System and Titan. CH4, H2O, and molecular hydrogen collision-induced absorption give Gliese 229b blue near-infrared colors. Its steeply sloped red optical spectrum also lacks the Fe-H and CrH bands that characterize L dwarfs and instead is influenced by exceptionally broad absorption features from the alkali metals Na and K. These differences led Kirkpatrick to propose the T spectral class for objects exhibiting H and K band CH4 absorption. As of 2013, 355 T dwarfs are known. NIR classification schemes for T dwarfs have recently been developed by Adam Bergasa and Tom Ball. Theories suggests that L dwarfs are a mixture of very low-mass stars and substellar objects, whereas the T dwarf class is composed entirely of brown dwarfs. Because of the absorption of sodium and potassium in the green part of the spectrum of T dwarfs, the actual appearance of T dwarfs to human visual perception is estimated to be not brown, but the color of magenta coal tar dye. T-class brown dwarfs, such as WISE-0316 plus 4307, have been detected over 100 light-years from the Sun, spectral class Y. There is some doubt as to what, if anything, should be included in the class Y dwarfs. They are expected to be much cooler than T dwarfs. They have been modeled, though there is no well-defined spectral sequence yet with prototypes. In 2009, the coolest known brown dwarfs had estimated effective temperatures between 500 and 600 kelvins, and have been assigned the spectral class T9. Three examples are the brown dwarf CFB-DSJ 5990-10.90-011401.3, ULASJ 133,553.45 plus 113,005.2, and ULASJ 3402.77005206.7. The spectra of these objects display absorption around 1.55 micrometers. Delorme et al. Have suggested that this feature is due to absorption from ammonia and that this should be taken as indicating the Tar-Y transition, making these objects of type YO. However, a feature is difficult to distinguish from absorption by water and methane, and other authors have stated that the assignment of class YO is premature. In April 2010, two newly discovered ultra-cool sub-brown dwarfs were proposed as prototypes for spectral class YO. In February 2011, Luhmann et al. Reported the discovery of a 300 K, 7 Jupiter mass brown dwarf companion to a nearby white dwarf. Though of planetary mass, Rodriguez et al. Suggest it is unlikely to have formed in the same manner as planets. Shortly after that, Liu et al. Published an account of a very cold brown dwarf orbiting another very low-mass brown dwarf and noted that given its low luminosity, atypical colors and cold temperature, CFB-DSJ 1458 plus 10b is a promising candidate for the hypothesized Y spectral class. In August 2011, scientists using data from NASA's Wide Field Infrared Survey Explorer discovered 6 white dwarfs, a Eurostar-like bodies with temperatures as cool as the human body. WISE data has revealed hundreds of new brown dwarfs. Of these, 14 are classified as coolers. One of the white dwarfs, called WISE 1828 plus 2650, was, as of August 2011, the record holder for the coldest brown dwarf, emitting no visible light at all. This type of object resembles free-floating planets more than stars. WISE 1828 plus 2650 was initially estimated to have an atmospheric temperature cooler than 300 Ca. For comparison, the upper end of room temperature is 298 kelvins. Its temperature has since been revised and newer estimates put it in the range of 250 to 400 K. In April 2014, WISE 0855-0714 was announced with a temperature profile estimated around 225 to 260 K and a mass of 3 to 10 mJ. It was also unusual in that its observed parallax meant a distance close to 7.2 A plus or minus 0.7 light-years from the Solar System. Spectral and atmospheric properties of brown dwarfs. The majority of flux emitted by L and T dwarfs is in the 1 to 2.5 micrometer near-infrared range. Low and decreasing temperatures through the late M, L, and T dwarf sequence result in a rich near-infrared spectrum containing a wide variety of features, from relatively narrow lines of neutral atomic species to broad molecular bands, all of which have different dependencies on temperature, gravity, and metallicity. Furthermore, these low-temperature conditions favor condensation out of the gas state and the formation of grains. Typical atmospheres of known brown dwarfs range in temperature from 2200 down to 750 kelvins compared to stars, which warm themselves with steady internal fusion. Brown dwarfs cool quickly over time. More massive dwarfs cool slower than less massive ones. Observational techniques. Coronagraphs have recently been used to detect faint objects orbiting bright visible stars, including Gliese 229b. Sensitive telescopes equipped with charge-coupled devices have been used to search distant star clusters for faint objects, including Tide 1. Wide-field searches have identified individual faint objects, such as Kalu 1. Brown dwarfs are often discovered in surveys to discover extrasolar planets. Methods of detecting extrasolar planets work for brown dwarfs as well, although brown dwarfs are much easier to detect. Milestones, 1995, first brown dwarf verified. Tide 1, an M8 object in the Pleiades cluster, is picked out with a CCD in the Spanish Observatory of Roque de los Muchachos of the Instituto de Astrofísica de Canarias. First methane brown dwarf verified. Gliese 229b is discovered orbiting red dwarf Gliese 229a using an adaptive optics coronagraph to sharpen images from the 60-inch reflecting telescope at Palomar Observatory on Southern California's Mount Palomar. Follow-up infrared spectroscopy made with the 200-inch Hale telescope shows an abundance of methane. 1998, first X-ray emitting brown dwarf found. Ka Alpha 1, an M8 object in the Shamalian I dark cloud, is determined to be an X-ray source, similar to convective late-type stars. December 15, 1999, first X-ray flare detected from a brown dwarf. A team at the University of California monitoring LP 944-20 via the Chandra X-ray Observatory, catches a 2-hour flare. July 27, 2000, first radio emission detected from a brown dwarf. A team of students at the Very Large Array reported their observations of LP 944-20 in the 15th March 2001 issue of the journal Nature. April 25, 2014, coldest known brown dwarf discovered. WISE J8558510.83-071442.5 is 7.2 light-years away and has a temperature between -48 to -13 degrees Celsius, making the dwarf the seventh closest star to the Sun. NASA, brown dwarf as an X-ray source. X-ray flares detected from brown dwarfs since 1999 suggest changing magnetic fields within them, similar to those in very low-mass stars. With no strong central nuclear energy source, the interior of a brown dwarf is in a rapid boiling, or convective state. When combined with a rapid rotation that most brown dwarfs exhibit, convection sets up conditions for the development of a strong, tangled magnetic field near the surface. The flare observed by Chandra from LP 944-20 could have its origin in the turbulent magnetized hot material beneath the brown dwarf's surface. A subsurface flare could conduct heat to the atmosphere, allowing electric currents to flow and produce an X-ray flare, like a stroke of lightning. The absence of X-rays from LP 944-20 during the non-flaring period is also a significant result. It sets the lowest observational limit on steady X-ray power produced by a brown dwarf star, and shows that coronas cease to exist as the surface temperature of a brown dwarf cools below about 2800 K and becomes electrically neutral. Using NASA's Chandra X-ray Observatory, scientists have detected X-rays from a low-mass brown dwarf in a multiple star system. This is the first time that a brown dwarf this close to its parent star, S, has been resolved in X-rays. Our Chandra data show that the X-rays originate from the brown dwarf's coronal plasma, which is some 3 million degrees Celsius, said Yuko Tsuboi of Chuo University in Tokyo. This brown dwarf is as bright as the Sun today in X-ray light, while it is 50 times less massive than the Sun, said Tsuboi. This observation, thus, raises the possibility that even massive planets might emit X-rays by themselves during their youth. Recent developments: the brown dwarf Ka 110,913 to 773,444, located 500 light-years away in the constellation Shamalian, may be in the process of forming a miniature planetary system. Astronomers from Pennsylvania State University have detected what they believe to be a disk of gas and dust similar to the one hypothesized to have formed the Solar System. Ka 110,913 to 773,444 is the smallest brown dwarf found to date, and if it formed a planetary system, it would be the smallest known object to have one. Their findings were published in the December 10, 2005 issue of Astrophysical Journal Letters. Recent observations of known brown dwarf candidates have revealed a pattern of brightening and dimming of infrared emissions that suggests relatively cool, opaque cloud patterns obscuring a hot interior that is stirred by extreme winds. The weather on such bodies is thought to be extremely violent, comparable to but far exceeding Jupiter's famous storms. On January 8, 2013, astronomers using NASA's Hubble and Spitzer space telescopes probed the stormy atmosphere of a brown dwarf named 2MASS J22282889-431026, creating the most detailed weather map of a brown dwarf thus far. It shows wind-driven, planet-sized clouds. The new research is a stepping stone toward a better understanding not only brown dwarfs, but also of the atmospheres of planets beyond the Solar System. NASA's WISE mission has detected 200 new brown dwarfs. There are actually fewer brown dwarfs in our cosmic neighborhood than previously thought. Rather than one star for every brown dwarf, there may be as many as 6 stars for every brown dwarf. Planets around brown dwarfs. The planetary mass objects 2M1207b and 2MASS J044144 that are orbiting brown dwarfs at large orbital distances may have formed by cloud collapse rather than accretion, and so may be sub-brown dwarfs rather than planets, which is inferred from relatively large masses and large orbits. The first discovery of a low-mass companion orbiting a brown dwarf at a small orbital distance using the radial velocity technique paved the way for the detection of planets around brown dwarfs on orbits of a few AU or smaller. However, with a mass ratio between the companion and primary and CHA high ±8 of about 0.3, this system rather resembles a binary star. Then, in 2013, the first planetary mass companion in a relatively small orbit was discovered orbiting a brown dwarf. Disks around brown dwarfs have been found to have many of the same features as disks around stars. Therefore, it is expected that there will be accretion-formed planets around brown dwarfs. Given the small mass of brown dwarf disks, most planets will be terrestrial planets rather than gas giants. If a giant planet orbits a brown dwarf across our line of sight, then, because they have approximately the same diameter, this would give a large signal for detection by transit. The accretion zone for planets around a brown dwarf is very close to the brown dwarf itself, so tidal forces would have a strong effect. Planets around brown dwarfs are likely to be carbon planets depleted of water. Habitability for hypothetical planets orbiting brown dwarfs has been studied. Computer models suggesting conditions for these bodies to have habitable planets are very stringent, the habitable zone being narrow and decreasing with time, due to the cooling of the brown dwarf. the orbit there would have to be of very low eccentricity to avoid strong tidal forces that would trigger a greenhouse effect on the planets, rendering them uninhabitable. Superlative brown dwarfs. WD 0137-349b, first confirmed brown dwarf to have survived the primary's red giant phase. In 1984, it was postulated by some astronomers that the Sun may be orbited by an undetected brown dwarf that could interact with the Oort cloud just as passing stars can. However, this theory has fallen out of favor. See also: brown dwarf desert, blue dwarf, dark matter, extrasolar planet, orange dwarf K-type main sequence star, yellow dwarf G-type main sequence star. References. External links: Hubble Site New Center Weather patterns on a brown dwarf, history, SS Kuma, low luminosity stars. Gordon and Breach, London, 1969 an early overview paper on brown dwarfs, the Columbia Encyclopedia, details, a current list of L&T dwarfs, a geological definition of brown dwarfs, contrasted with stars and planets. Neil Reed's pages at the Space Telescope Science Institute, on spectral analysis of M dwarfs, L dwarfs, and T dwarfs, temperature and mass characteristics of low-temperature dwarfs. First X-ray from brown dwarf observed, Spacef.com, 2000, brown dwarfs and ultra-cool dwarfs D. Montes, UCM, Wild Weather, Iron Rain on Failed Stars Scientists are investigating astonishing weather patterns on brown dwarfs, Space.com, 2006, NASA Brown Dwarf Detective ASA Detailed information in a simplified sense, brown dwarfs website with general information about brown dwarfs, stars, Car Alpha 1 stats and history, a census of observed brown dwarfs, Car 1998, Epsilon Indi Bar and BB, a pair of brown dwarfs is 12 Li away, Luminale, discovery of a planetary mass brown dwarf with a circumstellar disk, discovery narrows the gap between planets and brown dwarfs. 2007, Why Spectral Class for Ultra-Cool Dwarfs, N. R. Deacon and N. C. Hamberley, 2006.